I will be talking about the impact of high altitude on the development of fatigue during exercise today. I'm sure most of you, or some of you at least, know that the exercise that develops during, the fatigue that develops during exercise has two components. There is a peripheral component and a central component. Now, the peripheral component entails mostly metabolic events that occur distal to the neuromuscular junction with the consequence of a reduced force and power output in response to a given neural input. On the other side, there is central fatigue, which entails the central nervous system and the brain, which basically means that there is a reduction in the neural drive to the muscle that exercises, that contracts. So in other words, there's a reduction in central motor drive during exercise. Now, these two factors combine and affect exercise performance. We know now that there is a link between the peripheral component of fatigue and the central component of fatigue. I'm not going to talk about this link today. I will focus today on the question, what are the effects of acute and chronic hypoxia on the development of central and peripheral fatigue during exercise? Now, before I get started, I want to show you briefly what we do in order to quantify fatigue. We have a technique called supramaximal femoral nerve stimulation. What we do there is we stimulate the femoral nerve either magnetically, as you can see here, or electrically, and we evoke a twitch force, which we measure down here with a force transducer. These are electrodes which measure the M waves. But this stimulation here evokes a twitch force right at the leg, which is called quadriceps, potentiated quadriceps twitch force. And we do this before exercise in order to get an idea about peripheral fatigue, and then again after exercise, which I will show you in a minute. Now, central fatigue is another way that we look at, and we use the same technique. We superimpose a twitch during a maximal voluntary contraction, compare that to a potentiated twitch force, which we measure right after the maximal contraction. And that gives us the chance to calculate voluntary muscle activation, as you can see here, which is usually in trained athletes somewhere in the 90s before exercise. Now, they repeat this again as quick as possible after the exercise, and we usually see a discrepancy from before to after exercise. And this is what we use to quantify peripheral fatigue. And then in terms of voluntary activation, the difference from before, from before to after, this is what we use to quantify central fatigue. Now, one more thing that's important to realize before I get going with data is, and I'm sure you know this, the convective O2 transport in a human is determined by arterial oxygen content, abbreviated from here on out with this C(a)O2 times blood flow. And any factor that impedes on the oxygen transport during exercise exacerbates the development of fatigue during physical activity. So that's a very important thing to keep in mind. Now, the objectives of the talk today are threefold. First of all, I want to show you a few mechanisms, by far not all, which are responsible for altering convective O2 transport during exercise at altitude, and then associated consequences for the development of central and peripheral fatigue during exercise, and then consequences of a prolonged acclimatization to altitude on these relationships. Now, from here on out, I show you mostly data which we collected last summer in an expedition in Bolivia at an altitude of 5,300 meters roughly. We did 3 different trials. Now, this expedition included work at sea level, which was done in Eugene in Oregon, in the United States. And the 3 different trials that we did either in Eugene, acute hypoxia, and sea level experiments were done at sea level in Eugene. And the third one at altitude in chronic hypoxia, they all had one thing in general. That was the workload, which was 138 watts, and the duration, which was 11 minutes. So our subjects performed this very same exercise at all these, under all these 3 different environmental conditions. Now, the first trial was performed again at sea level, but the athletes were breathing about 10% oxygen, which this is the inspiratory partial pressure of oxygen here. that was done in order to simulate what we later will find, or did find here in Bolivia, about the same PiO2 as you can see here. Now that was followed by, again in Eugene, by the same trial, but under sea level conditions where they just did breathe room air. And then later on in La Paz at this altitude here, this is the inspiratory PO2. What we measured during these trials is central and peripheral fatigue with the femoral nerve stimulation technique, which I just showed you. We had transcranial Doppler to get an idea about brain O2 delivery. We had art lines in, and we had an esophageal balloon to quantify the work of breathing during exercise. So this is the beginning here in acute hypoxia. What you are looking at here is, again, 138 watts for 11 minutes, which you can see down here. And this is the hemoglobin saturation here, and this is the arterial oxygen content. The white triangles here, this is at sea level. So the exercise was not very demanding at sea level. The saturation didn't fall at all, really, during exercise. But when this was repeated in acute hypoxia, right from the get-go, it substantially dropped, and it stayed kind of low until the end of exercise. This was reflected in a reduction in arterial oxygen content, even at rest here, and then even further so during exercise throughout the remaining exercise bout here. Now, just simply based on this, I can tell you that convective O2 transport to the locomotor muscle is compromised in this case by a reduction in arterial oxygen content. And the brain O2 transport is also challenged by a reduction in arterial oxygen content. So that's one mechanism here. We also looked into the ventilatory responses and the work of breathing during exercise. Once again, same workload, duration here. And this is the ventilatory response here at sea level, so fairly easy, fairly light exercise intensity at sea level. Ventilatory response is below 60 liters per minute, really. When they repeated the exact same trial in acute hypoxia, we see a substantially increased ventilatory response, as you can see here. It doesn't even plateau, but it goes over 100 liters per minute. This was reflected in an increase in the work of breathing. This is the pressure time product. We have a little esophageal balloon sitting in the middle of the thorax, which is sensitive to pressure changes that occur during breathing. And then we can calculate the inspiratory muscle work, as you can see here. This is at sea level and significantly higher in acute hypoxia. So the breathing was a lot harder in acute hypoxia. Now, you might wonder at this point why I would tell you about the respiratory muscle work. How might the respiratory muscle work affect convective O2 transport during exercise? And I want to take you on a little side trip here in terms of that relationship. And what we are looking at here is this is esophageal and transdiaphragmatic pressure at 90% of the VO2 max of people exercising at sea level. This is one breath. This is the balloon that I was telling you about that sits in the thorax that is sensitive to these pressure changes. And upon inspiration, these pressures become negative because air now flows into your lungs. And then upon expiration, it becomes positive and you expire air. This is the transdiaphragmatic pressure. What we know is that this type of exercise, 90% of VO2 max all the way to exhaustion, is actually fatiguing for the diaphragm. So we develop diaphragm fatigue during exercise. Now, we have a little machine called a proportional assist ventilator, this thing here. And what this does is there is a little sensor sitting right here at the mouth. And when the athletes start an inspiration, that triggers that machine, and that machine pushes air into the subjects. And we therefore unload breathing. And when we put heliox through here, then we can also unload the expiratory side. So this is actually quite comfortable once you get used to it. It is an amazing feeling. It takes a little bit of time to get used to it, but then it's quite a nice thing. And what we can do is we can unload breathing during exercise, as you can see here. The intrathoracic pressure swings become less negative here, which is reflected in the transdiaphragmatic pressure. And what this does is it attenuates the development of respiratory fatigue, in this case in terms of diaphragm fatigue. And we can do the opposite. We can load the inspiratory muscles. We just put a little mesh on the inspiratory side, makes it harder to breathe in. and the inspiratory pressures become more negative. As you can see here, this is the esophageal pressure, and the transdiaphragmatic pressure becomes higher. And what we find is we can therefore accelerate the development of diaphragm fatigue during exercise. Now, Craig Harms used these two techniques, increasing the work of breathing, reducing the work of breathing, and manipulated respiratory muscle work during constant load bike exercise at about 85% of the VO2 max. And what you can see here, this is the work of breathing. This is 100%. So he made it harder with the mesh, or he unloaded it with the proportional assist ventilator. And what he found is that there is a link between how hard people breathe and the blood flow to the legs, Q legs. This is a limb blood flow, basically. So he found then that when the work of breathing was harder, the blood flow to the leg actually went down. When the work of breathing was easier, by unloading the respiratory muscles, the blood flow to the legs actually went up. What he also found is that there is a nice correlation between the work of breathing and leg vascular resistance. So in a way that when breathing is harder, leg vascular resistance goes up, and the opposite, it goes down when the work of breathing is attenuated. And there was a sympathetic involvement here. Norepinephrine spillover was correlated with leg vascular resistance, so indicating that the sympathetics are involved in this relationship. Now, the question remains, how do changes in the work of breathing change the blood flow to the leg? Is it maybe through the diaphragm fatigue that we see during exercise? There was, of course, more research done in this area, but the respiratory muscle metabolic reflex is the mechanism behind this thing, and let me explain how that works. During fatiguing exercise, this is the diaphragm here, during fatiguing exercise, there are metabolites accumulating with the development of diaphragm fatigue, and metabosensitive group 4 phrenic afferents increase their discharge frequency back to the medulla, to the central nervous system here, which in turn responds with an increased sympathetic efferent discharge, which causes limb vasoconstriction not only at rest but also at exercise. So now you see that the work of breathing has a huge impact on the amount of oxygen that's delivered to the legs, and therefore locomotor muscle exercise in acute hypoxia, where the work of breathing was so much higher compared to sea level, is also impaired by changes in limb blood flow. Question is, what actually happens to locomotor muscle and brain O2 delivery during exercise in acute hypoxia? Let's start with the brain O2 delivery. This is data from the transcranial Doppler, which you can probably not see it, but it sits right here. And what we measure there is the middle cerebral artery blood velocity. As you can see here, this is at sea level, and this is in acute hypoxia. Now, we work under the assumption that the diameter of this artery doesn't change with exercise or with exposure to hypoxia. This is a very hotly debated topic right now, and you can find arguments for both sides. It does change, it does not. For now, let me say it does not change. And we are able to calculate somewhat of an index of O2 delivery to the brain. Now, again, this is sea level right here, and when they repeated the exercise in acute hypoxia, there's a reduction in O2 delivery to the brain. What about leg O2 transport to the O2 transport to the leg? This is data from Eugene Wolfel here. He did submaximal constant load exercise at Pikes Peak, 4,300 meters. Exercise intensity was fairly similar to ours, about 50% of sea level VO2 max. And what he found is, this is at sea level. And when the same exercise was performed in acute hypoxia, the O2 delivery to the leg was actually reduced. Interesting in this data set is really that the VO2 of the leg was also reduced, so compensatory mechanisms which would probably have been available at this exercise did not kick in to assure a unchanged leg VO2. What happens to fatigue? Again, let me start with peripheral fatigue, where the O2 delivery to the periphery is reduced. What we find is, this is at sea level, this is the percent reduction from pre to post exercise in terms of twitch force. At sea level, the exercise did not cause a very severe level of fatigue. Actually, this was not even significant here. But when the identical exercise was repeated in acute hypoxia, peripheral fatigue was substantially exaggerated. Central fatigue, remember, O2 delivery to the brain was reduced, and what we found is that following the exercise at sea level, we did not find this is not significantly different from pre-exercise, so no central fatigue in normoxia at sea level, but in acute hypoxia, a huge degree of central fatigue. Now, as an interim summary here, I can say that the acute hypoxia decreases leg O2 transport and exaggerates the rate of locomotor muscle fatigue via a reduction in hemoglobin, in arterial oxygen content, mainly due to a hemoglobin desaturation. We see a reduction in limb blood flow, which is probably mainly due to the respiratory muscle metabolic reflex. And in terms of brain O2 delivery in acute hypoxia, that is substantially decreased, and the rate of central fatigue is exaggerated, and this is mainly due to a reduction in content. Now, the question is, what does prolonged acclimatization to altitude do to this relationship here? What are the effects of chronic hypoxia on the development of central and peripheral fatigue? This is where our subjects stayed. This is where they slept. This is little videos that we have to entertain them for a few weeks up there. Let's start with the hyperventilatory response and the hemoglobin saturation that occurs following a 2-week acclimatization to 5,300 meters roughly. This is again the ventilatory response. This is the hemoglobin saturation. And this is the exercise time. And as you can see, this is sea level. It was significantly increased in acute hypoxia. But now following a 2-week acclimatization, the ventilatory response was even higher. Now we are talking about a 2-fold increase in the ventilatory response to exercise. That was effective in bringing the hemoglobin saturation back. Alveolar ventilation goes up, hemoglobin saturation gets closer to sea level values again. What we also saw is an increase in hemoglobin concentration. This is at sea level, this is in acute hypoxia, and this is in chronic hypoxia. So hemoglobin concentration went up, and the combination between the increase in ventilation, which resulted in an increase in hemoglobin saturation, and this increase in hemoglobin concentration, they combine, and we actually normalize arterial oxygen content. Now, following 2 weeks of acclimatization at altitude, the arterial oxygen content is actually the same as it was at sea level. Now, what about the O2 transport to the brain? As you can see here, the velocity of the middle cerebral artery went down again a little bit from acute hypoxia, so a significant increase from sea level to acute, and then a small reduction again, but still a lot higher as compared to sea level. And the brain O2 delivery now in chronic hypoxia is right here, actually surpassed that what we see at sea level, and certainly what we saw in acute hypoxia. Now, these are very beneficial effects on convective O2 transport. So we see a beneficial effect on locomotor muscle O2 transport, mainly due to arterial oxygen content, and we see a beneficial effect on brain O2 transport, again, mainly due to arterial oxygen content. Now, these beneficial adaptations associated with prolonged acclimatization would insinuate that the development of central and peripheral fatigue are actually attenuated following a prolonged exposure to hypoxia. However, what we also found is that the respiratory muscle work, now we are looking at this here, this is chronic hypoxia, was once again substantially increased compared to definitely sea level, but also increased compared to acute hypoxia. And this happened despite the lower air density that you can find up there. And I just want to remind you that the muscle metabolic reflex, of course, played a huge role here, challenging O2 delivery to the brain, and therefore muscle O2 to the legs, muscle O2 transport is actually challenged by a reduction in limb blood flow that is secondary to this increased work of breathing here. Also, something that happens at altitude when you stay up higher here, and this is data from Mike Sander and Hansen, in 2003, they looked into the muscle sympathetic nerve activity that occurs or that's associated with a prolonged stay at altitude, and they found that MSNA from sea level to a few weeks at actually the exact same location where we were substantially increased. So higher sympathetic outflow up there, which is obviously a threat to limb blood flow. And therefore, the locomotor muscle O2 transport following chronic exposure to altitude is also challenged by leg blood flow here and brain blood flow up here, because the sympathetic outflow is a global effect. And here's what actually happens to limb blood flow during exercise. Again, this is sea level, white here. This is leg blood flow. This is sea level. And then we have acute hypoxia. The blood flow to the leg was not significantly different compared to the sea level exercise, but then following the acclimatization, where the respiratory muscle metabolism reflex and the increased MSNA, even at rest, played such a huge role, you actually see a reduction in the blood flow to the leg during exercise. So on the one hand, following prolonged acclimatization, you have an increase in content, which is actually recovered and improved over sea level values. But limb blood flow is now lower compared to acute hypoxia. And the question is, what is the net effect on locomotor muscle O2 transport following prolonged exposure to altitude? And interesting here is actually that the single leg O2 delivery is not significantly different in acute hypoxia versus chronic hypoxia. So this is sea level, this is acute hypoxia, this right here, and this is chronic hypoxia. So the O2 transport, despite these beneficial effects, is not really improved. Which leaves us with the question, so what actually happens to fatigue then during exercise? Again, the exact same exercise intensity and duration. Let's start with central fatigue. Remember, the O2 transport to the brain in terms of central fatigue was improved, and we actually found a significant improvement. This is acute hypoxia, this is sea level, so drastically worse in acute hypoxia, but then following a 2-week exposure, central fatigue substantially recovered, but there is still some central fatigue left compared to sea level. But better than in acute hypoxia. Now, peripheral fatigue, remember the O2 delivery to the brain, to the leg did not really improve. And so it's not necessarily surprising that we did not see a recovery in the development of peripheral fatigue following a 2-week acclimatization to altitude. So it's about the same as what we find in acute hypoxia. As an interim summary in terms of chronic hypoxia, I can tell you that chronic hypoxia does not improve leg O2 transport and the rate of locomotor muscle fatigue from acute hypoxia. Despite an increase in arterial oxygen content, there is a reduction in leg blood flow, mainly due to respiratory muscle metabolism reflex and an increased MSNA. And the net effect is a similar leg O2 delivery in acute and chronic hypoxia. Chronic hypoxia improves cerebral O2 transport and the rate of central fatigue from acute hypoxia, and this is mainly due to an increase in arterial oxygen content. And as an overall summary and as a conclusion, we can say that acute hypoxia exaggerates central and peripheral fatigue. Prolonged acclimatization recovers central fatigue, but fails to improve peripheral fatigue. Now, what does this mean in practical terms? Some of you might know that when you stay at altitude for a prolonged time, the exercise performance actually partially improves with a prolonged acclimatization there. So you expose somebody acutely to exercise, performance is down, 2 weeks later it's a little bit improved. And what our data suggests is that this improvement might largely be explained by the attenuated development of central fatigue during exercise, since peripheral fatigue didn't really change. And with this last slide, with showing people that I've worked with in the past, I want to say thank you very much. And I don't know whether we have questions. Later, okay.